Papito. Are you ready? Perfect. So today we're going to do a big general review about second 6 weeks. Again, every single topic that we will have in that presentation will be helping you all for the second common assessment. All right. So you need to review in this lesson plan. You need to review the first one. It's going to be Newton's law of motion. Who remember how many laws we saw for Newton's? Three. All right. Which one is one of those laws?
That anything in motion will stay in motion until
Okay.
something stops.
What law is that one?
First.
First law. Another one. Second law. All right. And the third law of Newton. We was talking about that in the second 6 weeks. Of course, we talked about the unit force, and the unit force was two-dimensional motion. Everything about that, maybe not in this review because I have another review for Monday, but we're gonna touch some specific and important topics in those two-dimensional motion. And the last unit that we saw, it's about Newton's 2 and talk about universal gravitational law. All right? In general, those are the major topics that we taught and learned in the second 6 weeks. I'm happy about third 6 weeks. I'm happy about third 6 weeks because we're going to talk about just two simple units, all right? But in the second 6 weeks, we get a lot of knowledge. Okay. Newton's first and third law. And you will pay attention that in these lessons goal, I have Newton's first and third law combined. And it's because the similarity, right, between those laws. It's because pretty much we don't use math for those laws, and everything is theoretical. All right? It's about concepts and definitions and define motion, nothing else, and what happened with motions and forces. Okay? Lesson goal. Describe Newton's first law and how it's related to inertia. It's not the same. Use vectors, and now we're going to use a little bit math to calculate the effect of force and object. A specific net force. What is that? So we're gonna review about that today too. And explain Newton's third law and how it relates to actions and reactions forces. That's going to be the first part of the class. Vocabulary for this class. Dynamic equilibrium. If you can write that in the corner of your notebook, you can research about that. Inertia, Newton's first law, Newton's third law, and static equilibrium. I'm not gonna clarify about dynamic equilibrium and static equilibrium because I remember that one of the presentation before this one, I believe that 2 weeks ago, you have the definition in your notebook. What's dynamic equilibrium and what static equilibrium means? And can I continue?
Yes.
And we're gonna waste time if I'm gonna stop explaining again what's dynamic, what's static. So just write in the corner of your notebook, find the definition of these vocabulary words, and everything is gonna make sense for you. Okay? Can I continue? Perfect. Forces. Who's gonna give me example of forces? Push and pull, good. Who else? Gravity, perfect. What else? Someone. That's below to gravitation. Friction. Gravity. And normal force. Those are the forces that we're going to talk in this class now. Alright? I'm not going to explain those forces now because you are seeing these forces since middle school. If you want to write these in the corner of your notebook, and you can research about the definition of those forces, well, what I'm going to do is use something that we learned like 2 weeks ago. And I call Freebody Diagram, or they call that in physics, to define some forces acting on that tube. Alright? Let's use a vector that is a magnitude and mathematical magnitude that describe direction and unit of a force. And a free body diagram, and let's try to figure out how many forces acting in that shoes. What happened when the dog just pulled these shoes? We get motion, right?
Yes.
And that is one of the forces acting on the shoes. Pulling, all right? Force of pulling. Yes or no?
Yes.
Another force acting on the shoes. Normal force. That's a positive or negative force?
Positive.
Positive, because the normal force always is going up. Opposite to other force. What's the opposite force there? To normal.
The one with the shoe.
This one.
Yeah.
Down. What is that force?
The negative.
But what is?
Is it the gravitation?
Gravity. Perfect. Force of gravity. That is a constant. Who remember the number for the force of gravity?
9.8
Uh-huh.
milliseconds squared.
Meters per second squared. 9.8 meters per second squared. Perfect. Positive or negative?
Positive.
Seriously.
Negative.
Oh.
Because it's going down.
Okay, you got it. Gravitation is going to be negative. So what will be the number for a normal force?
Same thing.
The same thing. According to Newton's third law, yes or no?
Yes.
Perfect. And what is the other force? We missed one force there. Say it. Friction. So when the dog pull these shoes, according to the free body diagram, we get friction from the floor to the left. And it's because to the left, how's going to be our number?
It's going to be negative.
Negative. So we can infer that force of friction. We can infer that every single forces acting down or left, our number is going to be what?
Negative.
Every single force right and up,
Positive.
positive number. Perfect. Let's continue. First law. Object at rest, stay at rest. Right?
Yeah.
But that's not inertia. That's a misconception. Okay? Object in motion, what?
Remain in motion.
Okay? And that is what we call in physics inertia. The inertia is the tendency of the object in motion and tend to stay in motion. And until when we're going to have that?
Until you apply force.
Until we apply an external force. Perfect. Object tend to resist a change in motion. This is called inertia. you want to take that note, I'm pretty sure that you have that note in your notebook. But if you, this is the simplified version of our previous class. This is the simplified version of our previous class. Okay? And remember, every single question on the common assessment about first law is not going to involve math. This, for physics, is theory. Everything is going to be described or defined. Nothing is going to involve math when we talk about Newton's first law. Can I continue?
Yes. Yeah.
Mass and inertia. Okay? And I have a question on the smartboard now. Which object require more force to move? Talking about the two elephants there.
The big one.
The big one? Why?
More mass.
Because this area has more mass. So we can say that more mass an object has the most inertia it has. Yes or no?
Yes.
The more mass in objects has the more inertia he has. Alright? Which object require more force to stop between the car and the truck?
The truck.
The truck. Again, more mass, more inertia. Calculating forces. Now I have a book at the top of the table using Freebody Diagram again. And let's calculate the net force acting on that book. Right now we have two forces acting on the book. Who's going to give me that? Using a normal force
And the gravitation because it's at rest.
and the gravitation because it's a rest. Alright? And I can say that the force acting on the book is going to be negative 20 Newton. This is just an example. According to Newton's third law, every action has an equal and opposite reaction. Yes or no?
Yes.
So the normal force is going to be what?
Positive 20.
Positive 20. Positive 20. Yes or no?
Yes.
Opposite equal reaction. Yes or no?
Yes.
If we apply basic algebra, 20 minus 20 newtons,
0.
our net force in this book is equal to 0 newtons. Means that that object doesn't have any motion. Yes or no?
Yes.
Perfect. You remember that, right?
Yes.
Okay. Let's use a free body diagram for that one. How many forces will be acting in that train? 3.
No.
Stop and think again. How many?
4.
4.
4. Perfect. One is going to be force of gravity. The other one is going to be normal force. Right? The force of acceleration and the force of friction. That's the opposite. Yes or no?
Yes.
And I'm going to give you some data. I'm going to say that that train has, because it's related with gravity, has a force in newtons that force of gravity in newtons is going to be 5,000 newtons. Alright? Write those numbers down. It's going to be 5,000 newtons
For what?
for the force of gravity here. This is going to be 5,000 newtons. The normal force is going to be what?
5,000.
Negative 5,000.
Negative. Are you sure?
How do you
No,
do that?
it's
It's
5,000.
not negative.
I
It's
told
supposed to be at the bottom.
Positive. Negative is this one.
Yeah.
Okay. Perfect.
Okay.
You follow?
Yes.
I try to see if you are awake. Alright? a force of acceleration of 2,000 newtons. And of course, the force of friction is going to be what?
Negative 2,000.
Okay, perfect. You got it. You're awake. This is going to be the question. What is the normal force? What is the net force acting in that train or object? And if that train has motion or not?
It has motion.
Has motion because the picture, right?
Yeah.
Makes sense for us. But can you give me the net force of the train? It's zero, right? And how has motion? What we can infer from that? If the net force of the train is zero, why we have a motion?
Because it doesn't have the balance forces, no?
Because what?
It's going to stop.
No.
Because it's keeping this constant speed, it's moving at. Can you hear me?
Because it's a constant speed. When we have a constant speed in object in motion, the net force acting on the object will be zero. You follow me?
Yes.
Perfect. Let's continue. Newton's third law. I'm just going to do the definition of the third law. I'm not going to stop here. Alright? It's going to be short. For every action, there is an equal and opposite reaction. Yes or no?
Yeah.
That is just the definition of that. You can research about Newton's third law. I give you Khan Academy, YouTube. There is a lot of examples of that, but I'm not going to stop there. All right? It's a lot that we need to talk now. So this is a general review, so I'm not going to stop there. I'm just going to jump into the next law. Newton's second law. Definition. Newton's second law states or describe the relationship between object, mass, and the amount of force needed to accelerate. Newton's second law is often stated as force is equal to mass times acceleration. Force given us by SI, System International, by Newton's, mass given us in kilogram, and acceleration in meters per second squared. Easy to remember, but too many people wants to do or be hard with this. We just do a basic algebra, my lovely triangle. Force is equal to mass times acceleration, and we don't need to memorize. We don't need to memorize three formulas. We just memorize the basic one. And if you're looking for acceleration, what force is doing to mass? If you're looking for acceleration, what force is doing to mass?
Dividing.
If we're looking for mass, what force is doing to acceleration? But if we're looking for force, what mass is doing to acceleration?
Multiply.
Perfect. Everybody's clear on that. Okay, you remembered everything about that law, so I'm not going to stop there either. Classwork. Hey, I'm going to give you 10 minutes to complete this. First one, second one, and third one. A person with a mass of 75 kilograms, it's accelerate to 3 meters per second squared. Question is, how much force was applied to him? A pitcher accelerate a baseball with a mass of 1.5 kilograms at 6 meters per second squared. The question is, how much force does this take? And the last one, Peter, it's a baseball with 500 newtons. and the ball is accelerate at 25 meters per second squared. What is the mass of the ball? Write that down in your notebook. I'm gonna give you 10 minutes. Free. Feel free. Start working. You can write the answer if you want. But my advice is write a word problem. You will not remember the data in the future. Yes.
Mr. A, I'm done.
Huh? Perfect. Now we're gonna jump to the two-dimensional motion. Actually, I'm not gonna start here so long because we get a lot of practice with this last week with the videos from Ingenuity. Yes or no?
Yes.
Okay? And we get a lot of practice with acceleration in two dimension. We talk about centrifugal acceleration. Yes or no? So what I'm gonna get from here is what we don't see in class. A little bit, not so deep, but I'm gonna review about what's one dimension. And I say back in the first 6 weeks that one dimension describes motion in a straight line. Two dimensions describe motion in a curved path, circular motion and projectile motion. And two-dimensional forces vector, equilibrium vector, and inclined planes. I believe that I showed you in class was an inclined plane. Yes or no? In the Freebody Diagram. With a 90 angle degree? Yes or no?
Yes.
So I'm not going to talk too much about that. Alright? What I'm going to do is explain what we don't see. The same displacement can be achieved in many different ways. Okay? I just want to say that instead of specifying a hidden and distance that take you from the origin of coordinate system to your destination, you could add also indicate how many kilometers north you need to travel and how many miles kilometers is. When we say magnitude and direction, we are in present of what? Vector or scalar? Vector or scalar? Magnitude and direction?
Vector.
Vector. Perfect. Because we have the magnitude, means that we have the how much, and we have to where, right? So that will be a vector. Perfect. In either case, you need to specify two numbers. And this type of motion is called two-dimensional motion. Of course, we're going to use vectors, and when we use vectors, we can manipulate the vectors, right? We can do addition with the vectors. You saw that in algebra too, right?
Yep.
Yes or no? Or you can subtract the vectors, all right? That is an example, and that is a simple formula that we saw in class. Remember that? dr equal to d2 plus d1. Actually, we can use sometimes to calculate a triangle, a Pythagoras theorem. Yes or no?
Yeah.
We saw that in class too? Yes. So let's continue. Can I? This important statement in that slide is the last one. That's the major definition about what two-dimensional motion means. Okay? Vectors manipulation that I said before. Those are the definition. If you want, just take quick notes about that. But to let you know that you can research about those two bullets that I have at the end. Vector addition, you can refresh about that for the second 6 weeks. And vector subtraction. I will make the assumption that you have read the details about vectors manipulation on the common assessment and review about that. Okay? Those are good examples, those pictures that I have there. That is basically more math than physics. Yes or no?
Yes. So,
Okay? Can I continue? Just write in the corner of your notebook, research about vector manipulation, or talk to Mr. Allen about vector manipulation. How we add vectors if you don't remember that, or how we subtract vectors. Right? Remember, physics and algebra 2, it's a combined class. So Dr. Allen can help you with that. You know? What is projectile motion? Or projectile motion. Remember that I have a big accent and Cuban accent. So, projectile for me, projectile for you. That is the same. Okay? For this class, lesson goal or instructional objectives. Anyway. Define projectile motion. And in this class, I'm going to give you different type of projectile motion. I'm not going to give you the formula because you have that in your notebook. Okay? But you can research about that. Projectile motion. Define, distinguish between the different type of projectile motion. Vocabulary. To research and define. Actually, I believe that you have this vocabulary already in your notebooks. Parabolic. Inertia, projectile, and projectile motion. Okay? Parabolic, inertia, projectile, and projectile motion. Type of projectile motions on the slide already. Horizontal, an example of that. Motion of a ball rolling, filling along of a level surface. Horizontal, vertical is always a constant. Vertical motion of a free falling objects, force due to the gravity, vertical components of velocity change with time. And parabolic, path traced by an object accelerating only in a vertical direction while moving at constant horizontal velocity. Follow me? Those are 3 examples of type of projectile motion. I'm going to give you time to take those quick notes. Yeah, be smart. Hey Jackie, take a picture. Can I continue?
yes.
Those are some formulas that we saw. You can take a picture of that too, or you can write it down. I'm going to give you time. Note that gravity there is 9.8 meters per second squared. But those are some formulas that you see in math. Those are some formulas that we work here, especially when we start talking about parabolic motion and two-dimension. Those that we have under there with sine and cosine. And we start talking about angles, yes or no?
Yes.
Okay. So if you miss some of those formulas, now is the moment you can write it down. Actually, the final product of some things that calculate the distance of the catapults that you build was in base of those formulas. Can I continue?
No.
Okay. Next. Class exercise. Let's see if we can answer these three questions. Okay? An object is fired from the ground at 100 meters per second at an angle of 30 degrees with horizontal. First question. Calculate the horizontal and vertical component of the initial velocity. After 2.0 seconds, how far has the object traveled in the horizontal direction? And the last one, how high is the object at this point? I will give it you. Sometimes after that, I'm going to show you the answer. Okay? I'm going to give you sometimes. After that, I'm going to give you the, for some of you, how we solve that. Anyone? Ready?
No.
I'm going to give you time. One, it's going to help you. This last topic on the class is going to help you with the assignment that I have in Echo that is due today. The gravitational one is due today. Well, pay attention now because I have some more problems. I have some formula that is going to help you with that assignment. Okay? Newton's law of universal gravitation, simplified version. This is the simplified version. Let's make that a real version, all right? Every object with mass attract every other object with mass. Simple, straight, nothing else. Example of that: moon on the air, planets around the sun. Yes or no?
Yes.
Okay, perfect. Newton realized that the force of attraction between two massive objects, and pay attention now, he just realized that increase as the mass of the object increase. So more mass, more attraction. What that means? That they have a direct relationship. More mass, more attraction. And decrease as the distance between those objects increase. So it's an inverse relationship in the distance. So don't matter how much mass you have a lot of distance between those objects, the force of gravity and the attraction, it's going to decrease. Okay? Do you need more time for that?
Oh, I got it.
Direct relationship with the mass of the object and indirect relationship with the distance. Of course, because that reason, the formula will be that force of gravity will be equal to the big G, or gravitation, that is the constant, and I'm going to give you that number now. Gravitational constant, sometimes refers as a big G, will be equal to 6.67 times 10 to the negative 11 power. And if you pay attention now, Newton's square, mass squared, divided by kilograms squared. Everything is a square. Alright? where mass 1 and M2 is the mass of the two bodies. We saw that? No, this period doesn't see that. So that's why I'm stopping. You saw it. Okay? M1 and M2 is the mass of the two bodies. Of course, in kilograms. R is the distance between them. Right. Okay? And of course it's going to be square too. Can I continue? The law of universal gravitation is an inverse square law. What that means, Mr. Abreu? Do you see that every single unit is a square? Yes or no?
Yes.
Yes or no?
Yes.
That means, because it's an inverse square law, if the distance double between the objects and the distance and the gravity, they are inverse relationship. If the distance double and it's an inverse square law, the force is not going to decrease double. The force is going to drop by 1/4. That means that it's not because the distance double 4 meters, all right, the force is going to decrease by 2. No. It's an inverse square law. So if the distance double, the force will drop by 1/4. Of course, if the distance triple, and it's square inverse, the force will drop in by 1/9. Because it's inverse square. And this is pretty much similar if we get a word problem, because we have a constant, we are big kids. This is pretty much to give me the numbers, and we're placing these numbers, replacing, performing the calculation, and then you will get in the answer. And the numbers in the word problem about laws of gravitational is going to make sense for you all. It's nothing hard. Okay? Distance, force of gravity divided by 100 times 10 equals force of gravity divided by 100. Can I continue?
Yes.
All right. And it's more class activity. Jim is attracted by Betty or to Betty. All right. You pay attention now. I'm going to give you the word problem and the solution. You will see that it's going to be the same. Okay. Jimmy mass is 90 kilograms. Close to tie, right? Okay. And Betty mass is 57 kilograms. If Jim is standing at a distance of 10 meters away from Betty, what is the gravitational force between them? Yes, we can do that. And the way that how we do that is simple. That is the formula, never change. The same that I gave you a few minutes ago. You got it? What is the mass of the M1 on the word problem? Because big G is a constant. So what is the mass of the M1? 90 kilograms. Perfect. All right. What is M2? Okay. And what is R squared? 10 meters. It's just, if you pay attention to that, and you perform that, you place the constant, brackets, right? 90 kilograms bracket, 57 kilograms bracket, divided by 10 meters squared. You place that in a smart calculator. At the end, you perform the division. Your final answer will be 3.42 newtons because it's a force of gravity. Of course, the unit has to be in newtons. You follow me? Something hard on that. We just replace numbers, guys. Alright? So now you can go to Echo. Open your Echo account and you will have an assignment about law of universal gravitational, and you can work in that. Because this classroom already complete all the final projects, right? So that's it. Nice class. Officially you are in a video for ladies. Okay. Newton's. Sir Isaac Newton's the universal gravitational law. It's simple. Not too many people get from these. Okay? We talked about this last class, yes or no?
Yes.
So, and you know that history from middle school. I'm not gonna jump and explain that something just fell into the air. Right? Come on. Let's go. Alright. So Newton's excellent idea. Now, you know, a brilliant, like if the force of gravity reach to the top of the highest tree, you know. Can I do over this again? Can I go over this again?
No.
No, right. I'm sorry for Plano campus.
Plano.
Yeah, but they saw that in the previous class. So Plano campus, you can research about this definition. I need to go on, all right? So, the falling moon, Newton's first law. An object, like the moon, will remain in motion in a straight line unless that acted or by outside unbalanced force, gravity attractions. The force that pull an apple to the ground also keep the moon in orbit. Make sense?
Yes.
It's the same force. The only difference between those objects is going to be what? How heavy they are. Or the distance between the objects. We talked about that in the previous class.
Yes.
Yes or no?
Yes.
Perfect. Yes or no?
Yes.
Okay. Newton's theory of gravitation confirmed the Copernican theory of the solar system. Alright? Objects spin around the center. And a planet's tangential speed allows the planet to orbit the sun without being pulled into it. Make sense?
Yes.
Newton's law of universal gravitation. That was the formulas that we saw in previous class when Fg means what?
The force of gravity.
Perfect. Equals to what? Big G. And I say that big G will be what?
The universal gravitation.
Okay, and it's going to be a constant, yes or no?
Yes.
Can someone find me the number that we talked about that in previous class? No, that's the gravity of the Earth. Huh?
1.68.
No, the other one. Last class, someone.
1.9.
No,
1.9.
no.
1.9.
Please, the constant, the big G constant. Okay, find it. Mm-hmm.
This is 6.67.
No?
You're going good. Go ahead. 6.67 what?
Times 10.
Uh-huh. Ándale, ándale. Thank God. Someone with something in the inside of the school. Perfect.
Hold on, so
And
what was it? 6 point what?
6.67 times 10 to the 11th power.
6.67 times 10.
That's a constant. And I say, in the word problems for this law, I will need to give you the mass of the object, the second mass. This is high school. I will need to give you everything. I will need to give you all the numbers. And of course, I'm not going to give you big G because big G is a constant. You just need to replace the numbers. You just need to perform the operation, the normal algebra, and you will get the answer. Yes or no?
Yes.
Perfect. Let's continue. Oh, you got it. Yes or no?
Yes.
Yes. Perfect. Do I have to go over the units?
No.
No.
Okay, let's continue. No. 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 We solved that already. Okay, class work. Let's do this together. Two students are sitting 1.50 meters apart. One student has a mass of 70 kilograms and the other has a mass of 52 kilograms. What is the gravitational between them? What is the gravitational force between them?
It's 1.55.
I don't know. Go to the north. Just try to write that down on your notebooks or just get the data out from the smartboard and perform the math. Let's use the formula that we just saw a few minutes ago. The formula that we saw back on our previous class. Let's go. I'm going to give you 5 minutes for that one. It's already on the video, so they can. For Plano campus, you can try to use the formula and the constant for big G. Let me see. This is the other one. A gravitational force between objects of equal mass. Okay, now you have the same mass. It's 1552 newtons. All right. When the objects are apart 10 meters, what is the mass of each object?
That's the little triangle you did, right?
Go ahead.
So wait. It's 1552 divided by 2.
Here's a motion of 55.2.
He said 2000.
I don't know. That's a Newton, that's a force, that's not mass.
Que ya se está infestando.